Welcome to this lecture series in linear algebra. In this lecture, we will define and prove the existence of the minimal polynomial of an endomorphism. The minimal polynomial will be a central object of inquiry in the entire course, and it is actually a very powerful tool. So let's recall what we need. We will need to know how polynomials interact with endomorphisms. So given an endomorphism T on a vector space V, and given a polynomial over the base field, we can define a new endomorphism on the vector space via this recipe. So if the polynomial looks like this, then we define the new endomorphism in this fashion, where t to the power 0 has to be interpreted as the identity endomorphism. Alright, so we discussed this at length, and we will need the division with remainder theorem, which says that if you have a polynomial px and another non-zero polynomial dx, then you may write it as follows, where rx has degree strictly less than the degree of dx, where we need to remember that the degree of the zero polynomial is minus infinite. Alright, we will also need the notion of a monic polynomial. A monic polynomial is just a polynomial whose leading coefficient is 1. So it is in particular a non-zero polynomial. Okay. So first we will prove a lemma that we have essentially proved earlier when we were proving the existence of an eigenvalue of an endomorphism on a complex vector space. But it is not harmful to repeat the reasoning. At the very least, we did not prove that result in abstraction, meaning in full generality, even though the proof does not change at all. So what is the result? Fix an endomorphism on a vector space V, completely abstract vector space over an arbitrary base field, just that it is finite dimensional. Then there is a monic polynomial Px such that P of t is 0. And when this happens, we say that t satisfies the polynomial Px, or Px is satisfied by t. Just some terminology. Alright, so let's prove it. And in fact, since you've already seen the proof of it, it might be a good idea to pause the video and rediscover or reconstruct the proof for yourself. So now, let's say, let n be the dimension of the base space, and hence n square is the dimension of end V. All right. And let consider the following endomorphisms on V. And the point to note is that these are linearly dependent. Why are they linearly dependent? The dimension of this vector space is n square, while these are more than n square. So they are linearly dependent, and hence there exist scalars, such not all 0, such that the corresponding linear combination is 0. So the upshot is the following. The upshot is that there exist scalars beta 0 to beta m, with beta m being non-zero, such that this linear combination is 0. So what is going on? Well, here we had some scalars such that the corresponding linear combination is 0. Since not all of them are 0, there has to be one, you start scanning from the right hand side. At some point you will arrive at a scalar which is non-zero, and that is kind of where we start the list from the right hand side. So I'm sure you were able to deduce from this statement, It is just primarily a change of notation, but it is useful that this last one is non-zero. Useful how? This implies that this is the case because all we have done is we have divided both sides by beta m. And now if we define the polynomial px as this, then p of t is 0 because that's exactly what this equation is. So that's the proof. That's the proof of this very nice fact. And let us proceed. So now we can define the minimal polynomial. So suppose we have a vector space, and for simplicity, assume its dimension is at least 1 because otherwise things are kind of backwards. And fix an endomorphism on V. And now collect all those polynomials. So those polynomials which are first of all monic and hence already non-zero, which are satisfied by T. And by the previous lemma, we know that this is not empty. This is exactly what the previous lemma says, that this set is not empty. Okay? And now, let Mx be an element of smallest degree in S. So we have a non-empty set. Each element here has some degree, which is an integer. That degree could be, it cannot be 0 because if the degree, I'm just making a side remark. No element here has degree 0 because if you have, let's say, a monic polynomial of degree 0, then it's basically this constant polynomial 1, and it cannot be satisfied by an endomorphism. So everything here has degree at least 1. And what we are doing is let's just pick one element with the smallest degree. A priori, there could be multiple such elements, but we'll get there later about how unique this is. So just pick one element of smallest degree. It exists by the well-ordering principle if one wants to be completely formal. So now the claim is this element that we chose divides each element of S. The element of smallest degree, an element of smallest degree or any element of smallest degree divides each element of S, and this is very easy. So let Px in S be arbitrary. By division with remainder theorem, we have Px equals mx qx plus rx for some qx and rx with degree of rx strictly less than degree mx. So that's the division with remainder theorem for polynomials. And now what we have is, now by the above equation, we have pt equals mt qt plus rt. But pt is 0 because px was chosen in S. Mt is 0 because mx is also an element of S. So these two are 0, and hence we conclude this implies that rt is 0. Right? So if rt were a non-zero polynomial, if rx was a non-zero polynomial, then we would have a polynomial of smaller degree, which is also in S. How? Rx is perhaps not monic, but if it is a non-zero polynomial which is satisfied by T, we can again forcefully make it monic and retain a polynomial of the same degree as that of R, which is satisfied by T. And hence in S there would be an element of degree even smaller than that of Mx, because the degree of, what have I written? This is degree Rx. Because the degree of Rx is smaller than degree Mx. So once again, if Rx were a non-zero polynomial, then we would have a polynomial of degree smaller than Mx, which is non-zero and satisfied by T. And hence we can forcefully construct a monic polynomial with the same degree as that of R, and hence degree strictly smaller than that of Mx, such that it is monic and satisfied by T, and hence a contradiction because Mx was a polynomial of smallest possible degree, which is monic and satisfied by T. So this kind of reasoning we have done multiple times. So the conclusion from this is that Rx must be 0, which is to say that Mx divides Px. So Rx is 0 is basically saying that Mx divides Px, and that is what we wanted to show, and that's it. So this is done. And an instant corollary of this result is that there is a unique element of smallest degree in S. Because if you pick two elements of smallest degree in S, they are both monic polynomials which divide each other. That's what this lemma says. So if two monic polynomials divide each other, they have to be equal. So that's it. That proves that this polynomial is unique, and this is called the minimal polynomial. So let me just write it here. This is called the minimal polynomial, and it is now legitimate to call it the minimal polynomial because we have shown that it is unique. Minimal polynomial of T. So this minimal polynomial is of course sensitive to which endomorphism we are playing around with. Okay. So there is a unique element of smallest degree in S, and that is called the minimal polynomial of T. And let's just take a very trivial example. What is the minimal polynomial of the identity endomorphism? If you just think about it, it is equal to x minus 1. So x minus 1 is the minimal polynomial of identity, because if you substitute identity here, you get identity minus identity, which is 0. Okay. So basically the summary is this. If T is an endomorphism on a vector space, then there is a unique smallest degree monic that is satisfied by the endomorphism, and this is called the minimal polynomial of the endomorphism. It exists is what we just proved. Okay, so let's see an example. We have this favorite 90-degree rotation map, which sends E1 to E2 and E2 to minus E1. Then what is the minimal polynomial of T? How do we compute it? So to compute the minimal polynomial, first we will, there are several ways to do it, but here is at least one way. So we know that, so T square E1 is what? This is equal to T of T E1. This is equal to minus E1. And what is T square of E2? This is equal to T of E2, which is T of minus E1, which is equal to minus T E1, which is that. So therefore, what this says is that T square E1 is minus E1 and T square E2 is minus E2. Therefore, T square is equal to minus identity, right? Because it fixes the basis elements, up with a minus sign. So T square must be minus identity, and thus T satisfies the polynomial Px, which is defined as x squared plus 1. So T satisfies this polynomial. That's what this equation tells us. And now the minimal polynomial, whatever that might be, should divide this, because the minimal polynomial of an endomorphism divides every monic polynomial that the endomorphism satisfies. But what are the monic polynomials over the reals that divide this? Only this one. Because if there were a monic polynomial that divided this of smaller degree, that would be a degree 1 polynomial, and hence this would have a root in R. But this does not have a root in R, and therefore this is the only monic polynomial that divides this. Apart from the constant polynomial 1, of course. So therefore this is the minimal polynomial of the endomorphism T. So yeah, I think that's it. And as usual, like, comment, share, subscribe, and I'll see you next time.